I would say it's a very important topic because how many of you, you're mostly modelers, right? How many of you have used only data that you collected yourself for your models? Oh, so you don't use any other data, right?
What?
You don't use any other data in your models collected by others?
Lots of them.
Yeah, okay, all right. So how often do you run into a situation when you need to bring data from others and you are not quite happy about how these data are organized, or you don't understand everything related to this data? That also happens quite often, and the goal of the work that I'll be trying to tell you about is to figure out how you make sharing of data sets and also of models possible, and make it such that people, when they get this data, they understand where the data come from, what this data describe, how is it possible to bring this data into their modeling systems, and make some scientifically sound conclusions from it. So the outline, I'll just mention briefly where I come from and what my projects are about, and then talk about how people develop standards. You have heard about water markup language and NetCDF, and these are just two standards that are popular in this community, but there are lots of other standards and best practices, and there are a fairly large group of people that work on procedures of how to make, how to look at use cases, develop what is common among different use cases, and standardize best practices, and make it into international conventions and standards. And then talk about the group that I'm co-leading, which is called Hydrology Domain Working Group of Open Geospatial Consortium and WMO, that developed water markup language and is working on extending it to other areas. Depending on how much time we'll have by then and how brave the audience is, we can dive into XML. How many of you have heard of XML? Okay, great. So we may not want to dive too deeply into that, but I'll show you how it looks like. And then we'll talk about how you share models, which is a lot crazier even than trying to share data sets. San Diego Supercomputer Center is one of the two largest supercomputer centers in the US. It has, of course, big machines that do a lot of so-called heroic computations. Mostly the focus is on how you feed a lot of data into computation. So one of the key machines is so-called Flash Gordon. It's the biggest flash drive in the world, like the biggest thumb drive that you can think of, several terabytes, and that allows very fast I/O between data and processors. But another type of work is cyber infrastructure, how we develop systems where there are multiple data providers, multiple providers of compute resources, and they all try to work together to solve some problems in sciences, in hydrology, in environmental science, biology, and so on. And my group specifically works on spatial information integration issues, on GIS, spatial data standards, too fast, and some of the projects are listed here. Hydrologic information system that Luis just mentioned, that's something that's we've been working on for the last 8 years or so, and it's developed to be probably the largest hydrologic information system in the world, with about 115 different services that go into it, and a fairly large catalog of hydrologic data. There are several other projects that deal with developing cyber infrastructure for the entire geosciences, a new initiative at NSF called EarthCube. I've been also working on a lot with neuroscientists when you need to share data about the brain. It's like sharing data about GIS data. There are multiple people who photograph brains, and they need to connect based on the location in the brain. So that's, these are a few things that we do. And a big part of development infrastructure and cyber infrastructure is to settle on some agreements about how different systems should talk together. Essentially, as Alfred Whitehead said a long time ago, we need to stop thinking about some things that machines well, there were no machines at the time, that should be done without thinking too much about that. If there are standard procedures, like you plug your computer in a network and you expect electricity to happen. If you plug some data into your model and hope that this model will work consistently, this is the type of environment we want to develop, and that's what DRIHM is also working on. Again, as Luis mentioned, we have a collaboration between the European part of the project, DRIHM, and the US part. So there is DRIHM to US on the European side, and on the US side, the project is called SCHEME, Standards-Based Cyber Infrastructure for Hydro-meteorology. These are fairly small projects, and the goal is to figure out what infrastructures exist at several levels. At the level of high-end computation, where there are systems like PRACE in Europe and EXCEED in the US. At the level of sharing of hydrologic and meteorological data, where on the US side we have quasi-HIS, quasi-hydrologic information system. On the US side there are multiple projects, but including DRIHM. And on top of it there is WRF and WRF Hydro that you will hear about in this workshop. So mostly I'm going to talk about this space, OGC standards, and how they bring different types of computations together. Systems need to be interoperable. I probably don't need to preach it to the choir. We need to achieve the ability of two or more systems to talk to each other at several levels, exchange information in a consistent manner and reliable manner. Why it is important? Because certainly there are disasters, not only natural disasters, but very much man-made disasters when people don't happen to coordinate at the technical level. Mars orbiter story, you may have heard about that, when a fairly expensive program to send Mars to send satellites to orbit Mars, and then it fell on the Mars surface because there was miscomputation. Some part of it was done in imperial units, and part of it was done in metric units. You may have heard a story about the glider incident. Have you heard of a glider incident? Okay, there was a story with Canadian Airlines that flew like across Canada, and that was a time when they transitioned from imperial system to the metric system, and they filled it about in pounds, and they needed to be in kilograms. So about midway, somewhere in the middle of Canada, fuel was lost. Both engines stopped. It was Boeing 767. Fortunately, the pilot was a glider, so a professional glider. So he glided this from 10 kilometers down and landed the plane. And since then, there were some additional checks and tests were installed in the system. But for such complex systems to operate, we need to be able to look at all possible connections and misconnections. And that also happens in hydrology. So let's look at a common situation. You are trying to do a model, and you need flow data. And tell me how similar or dissimilar this is to your experience. You're a modeler. So you call some guy on the other side and say, you need upper Derwent flow readings for my geochemical model. So there's a guy on the phone who says, I've got one side, and in about 10 minutes, you get data. Can you see the data? Well, there's actually some numbers here. That's what sometimes people refer to as dark data. You get something, but you don't quite understand what it is. This is comma-separated values, and you can tell that probably the first one is date, and then it's followed by some numbers. In 10 minutes, the guy calls back and says, I got the data, where is the site located? Well, that's an easy question. What are the coordinates? Then a lot of investigation around, paper shuffle. The coordinates are given. What reference system? That is already a tricky question, as you know. And what sensors is used? So what sensor is used? There is some answer. How accurate is that? That's a question about accuracy is a conversation killer, as you know. You don't get an answer. And that's the end of the conversation. So this is a slide from Australia, and we hope it only happens there, of course. But I've heard that in other parts of the world it may happen as well. So in response to that, we try to come up with a common description for hydrologic data so that this data could be exchanged with others in an unambiguous way. So in a way that would be easy for you and for computers to interpret. And you may have seen, or you may have missed, that's all right too, announcements of WaterML2 adoption. About 2 years ago, that was the first ever international standard for exchanging hydrologic data adopted at the international level at OGC. So there's been a bunch of press. And we'll run through this fairly quickly. And the idea is that now once this standard gets adopted by software vendors and by providers of hydrologic data, it will be easier to connect analysis tools and modeling tools with a lot of data that will be available in this format, rather than a situation when we have multiple data sets but available in all sorts of different formats, and you will need converters, and you will need some additional knowledge in order to understand and engage these data sets. There are lots of benefits associated with open standards. There's no single group that would control it, facilitates competition, innovation, and so on. And if you try to build an infrastructure where different systems talk to each other, you need to come up with some agreement. And that agreement may as well be at the level of international standard, because that will give it some aura of longevity and support. The group that does it is called Open Geospatial Consortium. How many of you have heard of OGC? Some of you. Very good. So Open Geospatial Consortium is so-called standards development organization that works with W3C and with other groups, and it's a club of about 500 members. 480 was the number of 2 years ago. We get together regularly 4 times a year in different parts of the world, and there are separate meetings for different groups as well, to see what are common problems in data exchange and what can be established as best practices and agreements for exchanging data, and eventually support moving these best practices into standards. This is a distribution by, so you would see that mostly people come from commercial center, but also from government and academia, and where did it go? And it's dominated, of course, by Europe and North America. What they do, you may have, again, remember some of these abbreviations. WMS stands for Web Mapping Service. When you go on the web and you try to compile your map from multiple images, right? These images would be served as WMS maps. Web Map Tiling Service, you know, when you zoom in and zoom out on Google, you get these rectangular pieces of maps. So there's a standard way of serving this type of data. Web Feature Service, when you request a source to get you coordinates of a particular object, and these coordinates will come in a given coordinate system as numbers, so that you can work with the geometry, and a few others. Specifically for the field that deals with observations and with hydrologic, meteorological type data, there are several standards in this domain, including sensor modeling language, observation and measurements that specifies how different types of information should be formatted, and a few other services. Then, and this is closely related to models, you may want to invoke your models on the web. In that case, you would want to send some request to a web service asking you to compute a model or compute a part of a model and give you and return results. There's a standard to do that for spatial type services called web processing service. and a bunch of web processing services can be chained into a workflow. There are some useful parts of the standard that allows you to, you send a request and then tell the server to leave the result on the server so that the next request would operate on them. In this case, you don't need to bring the results back each time, so that will be more efficient. You can also check how, check the status of execution. So this is a good standard, and there are lots of vendors now implementing it. Well, I probably should avoid saying things like good standard or not good standard, because it's there are lots of opinions. Well, if you join OGC, you will see that it is a very opinionated group, and there's nothing perfect. There is always movement to something better. But nevertheless, there are more than 700 products that implement these standards, and you can go on the website and check what are free, open source, or commercial solutions for any of the standards that you may want to use. Like that's one example, Digital Globe, and if you look at cloud services, you'll see that it serves web feature services and WMS, and tiling service and coverage service. So lots of data providers would have a bunch of services that would be standards compliant that would be available from them. And another group that we work with is called WMO, World Meteorological Organization. You must have heard of that, right? Okay, so under both of them, in 2007, 2009, there was a fairly long process of negotiation. A group was started called Hydrology Domain Working Group, which has the mission to develop standards for water data. In fact, there have been a bunch of different specifications that people have used to share data. There was one in Australia, so-called water data transfer standards. There were several in the US. There were some standards in Europe. They were not quite compatible. They had different conventions about semantics, about structure, and that made exchange of data quite difficult. So how this group works, we get together, as I said, at least 4 times a year, and try to invite presentations about different projects and trying to see what are the best practices and most interesting activities in the space of data, of hydrologic data sharing, trying to see what would be the next set of needs for sharing hydrologic data. For example, the first one was obvious, how you take time series and format in a way that consumers of time series, of hydrologic time series and meteorological time series would understand what this data mean without necessarily going back to you and asking, what did you mean when you sent me this package? So there are some standards or sample specifications put forward, and there is a group that there are several groups usually come together to work on interoperability experiment. You take the specification and try to run it for a specific use case. For example, exchange of groundwater between, in the Great Lakes area, between Canada and the US. They have used different systems, but in order to run groundwater models for the area, you need data from both. And so you need, ideally you would have a standard format that both systems would support so that you can interface this with ModFlow and other models. Another example was exchange of surface data, surface water data across the Rhine River between France and Germany. Again, different systems in France and in Germany, and once they started using, or they're now converting to WaterML2, then it would make running hydrologic models easier. So after such an experiment is done, there is an engineering report prepared, and that gives some information about how specification needs to be amended, and eventually it comes up for a vote as a standard. Brief history. Well, we started in 2007, as I said. I've been working with the group called QUASI, Consortium of Universities for Advancement of Hydrologic Science. And in 2007, we submitted we developed a specification called WaterML1, presented it to OGC, and that was followed with a bunch of additional meetings where eventually we decided to start a bigger group that would bring people from all over the world. And in 2002, WaterML version 2 was adopted that inherited some features of WaterML 1, but also was based on so-called OGC-based standards, one of them being observation and measurements spec. So WMO voted to adopt or voted to recommend adoption of these standards by member countries in 2012, which means that eventually member agencies of WMO will be expected to publish their hydrologic data in this standard. That would mean that if DRIHM infrastructure will know how to read WaterML2, it will be compatible with a growing set of data available through this standard. So how this whole system is supposed to work? Imagine that you have many different types of data sets and you can access them via services. Ideally, this would be standard set of services rather than a bunch of homegrown and no description type things. But this is certainly not sufficient, right? First of all, you do not connect to your specific server. You want to connect from any computer to any service, right? Then it turns out that it is not sufficient to declare that you can send a request to get observations and get observations back. You need to also describe what type of observations you are getting. And this is where we need hydrology-specific application schemas. Essentially, your client, let's say, it's your model, WRF or some other model that has, it's here, that has some notion of the format and content of the data that it wants to get. It has to match with the format and content of the data that has been provided by the data provider. So ideally, if they would map to a common hydrology application schema, that would make the translation easier. Which means that it's not just communication between servers and between your client applications and different kinds of servers. There also should be an agreement about the structure and content of the data. So I'm asking information about catchment data or time series data. The system should understand what time series is, and that is done by specific hydrology APIs. And that is still not sufficient, because what we really want is to, when you're asking for information about specific catchment or specific gauge station or specific event, you want the other side to understand that it is this exactly event or that specific gauge station that you know about. So ideally, you would reference the same definition of catchment or the same definition of event, which would be stored somewhere else. So ensuring that you're talking about the same thing is what people refer to, or what people are trying to address in the semantic web community. And there are many ways to, well, I shouldn't say many ways. There are some ways to do that. Ideally, you would set up some kind of semantic servers that both consumers of the data and providers of the data would refer to ensure that you are actually talking about the same thing. So is it the same, as I said, catchment or river or stream or so? Yes. A few words about the project that Louis started with, hydrologic information system. It is fairly simple, I would say, if you look at the general outline. We have a bunch of Hydro servers. This is software stack that you can download from our servers and install on your machines. That would allow you to take hydrologic data or any type of time series, load them into a database on the server, and then configure web services over that database so that when you want to extract this data, you would send a web service such as get values or get sites that you have. And you will get an XML file that will contain information from that server. Another part of it is a central catalog. Imagine that we have hundreds of servers all over the world, and you want to quickly search all the information that is available for, let's say, for a particular area. And that area, let's say, in Madrid, there may be multiple groups that collect water data. If you look at the US, for example, only at the national level there are 19, I believe, federal agencies that collect water data, and they don't talk to each other. So if you want to get data for a particular area, you may want to query what is available from USGS, US Geological Survey, what is available from Environmental Protection Agency, Bureau of Land Management, Department of Agriculture, and many others. Not to mention there are states, counties that all collect their data, not to mention universities that have all sorts of research projects, and they may have some data of interest for the area that you're working with. So how would you find out what is available? If they publish Hydro servers or subscribe to our schema, then we grab metadata from these services and store them in a central catalog so that when you ask, I want information about pH measured in, or discharge measured in this area between such and such dates. It will figure out which of the servers published by which organizations have this data, and then you will be able to formulate a request to each of the servers, knowing that you will get some useful information from them. And there's a client application. There's actually more than one client application. I mentioned that it's the biggest information system in the world, not because we accumulate all the data in our system. All the data are distributed. If it is US Geological Survey, they manage their data, but we just index what they have. If it's EPA, the same. So we have about 32,000 variables, 3 million sites where something has been measured, and more than 300 billion data points. As I say, I believe it's fairly simple system to use. I used to give like 2 or 3 day introduction to this system and training, so I'm not going to do it at that length now. If you have questions, I'll be able to answer later. So the suite of standards that Hydrology Working Group is working on, first of all, is water-markup language part 1, water quantity, how you describe time series, how you describe different types of time series, could be cumulative time series, could be instantaneous time series, could be other types. Next thing is how you describe ratings and gaugings. So in order to understand discharge, you need to be able to have rating curves. These rating curves are developed differently, and information about these rating curves is not consistent across different providers. So that is an attempt to standardize this type of data. Next part is, so that is almost done. So this is voted as standard, that is almost done, and will be voted as standard fairly soon. Part 3 is water quality. With water quality, we have quite a different story because the information here is, we have to deal with very large vocabularies. If you look at a collection of parameter codes that US Geological Survey operates, there will be about 10,000 different variables. Environmental Protection variables, Environmental Protection Agency in the US has another 10,000 variables that they collect, and these names do not match. Right? Some of them will be the same, but it takes work to actually match the variable names. Not to mention that the construction of these names is also quite different, and USGS it's traditionally designed such that variable name includes the root name, for example, discharge, but also includes units, includes medium in which it is collected, and a few other things. In EPA, it is somewhat more structured. So the notion of what a variable is also different. A few additional developments. WaterML part 4 will be groundwater. That is going now through second interoperability experiment, and the results will be formatted as a best practice and proposal for a standard. So-called river markup language is being developed to describe river geometry as a candidate for another standard, and this will be all part of the suite of WaterML, of water-related standards that the group is working on. Another interesting development that happened is that once WaterML 2 was developed, meteorologists came in and said, look, we are looking at time series in pretty much the same way as you guys. So if you remove anything that is related to hydrology, like hydrologic measurement points or water measurement points, we will use the same. So the decision is now to abstract everything that is hydro-related from the WaterML standard and come up with a time series markup language, which will be common across several observational fields, including hydrology, meteorology, and others. And so the group is now being set up within OGC to work on time series ML. Okay, so that would be, I'll run through this quickly because well, essentially, the message here is we're trying to get from the dots to understanding the curves, right? So information about points, what you collect points is not enough. You really want to look at continuous observations. And yeah, something like that. And there are several ways of, several mandatory things that you need to use to describe your time series. At a point, these are very common that are being provided by some agencies, and this is also what you need to take into account when you try to bring this data into a model. There are many different types of interpolations that can go in. Data can be continuous, discontinuous, instantaneous totals, average and preceding interval, maximum, and so on. And this information is not often conveyed. So you get your CSV file, but you don't really know what kind of measurements are these. In WaterML, these must be explicit. Yeah, so you would have different types of data. Explicit material, let me skip that, all right? If you will have questions about XML, I'll be happy to show you, but essentially, there's some model of how you describe points, where you do the measurements, some structure of information that you want to relay about time series, and that includes time series is essentially timestamp and a value, but also it has to have qualifiers, also it has information about location, information about who has done it, what detection limit was, and variable, and so on. And ideally that should be specified in a way that is compliant with previous standards so that we can reuse the libraries and we can reuse code developed elsewhere, and also connected at the easily integrated with other types of systems. For example, if you have multiple packages or multiple specifications that deal with the same representation of location, it would be easier to combine these different fields based on location. So location is described in GML, Geography Markup Language. Anybody heard of that? Yeah. Geography Markup Language, which is a common OGC standard, and since this is WaterML2 is also an OGC standard, we use it so that it will be easier to integrate with other documents developed in similar standards. Okay, so I'll quickly move on to another thing because we haven't really talked about models. I'm not a modeler. I used to do simulation models long time ago, and these were not related to water. But we have a project in one of my projects has this wonderful name. It's an abbreviation, right? Synergy stands for Community Inventory of EarthCube Resources for Geoscience Interoperability. EarthCube is a new initiative by NSF. It's supposed to be a fairly large initiative that is trying to develop infrastructure for integrating different types of geoscience data, models, research results, and so on. So if you are working in geochemistry or hydrology or meteorology or paleogeography, some other fields, you should be able to reuse some components that can be developed in other geoscience resources. And if you're trying to build more comprehensive models, the idea is that this infrastructure would help you do that. But the first step is to figure out what exists. And I believe when you work with models, you typically work with just one family of models, right? You don't often switch to other things. It still would be useful to know what other models exist and what people have done with it. And that information is not quite available, as it turned out. It may be easier to find data sets developed by different agencies. It may be easier to find, let's say, hydrologic time series served by USGS, collected by CHIMA, or collected by other groups. But if you ask if there is any catalog of models, even models that are used by folks in this room, I'm not sure you can point to one. In fact, there will be one eventually, because Quillan is working on it. But it is ready to go. So you will talk about it, but I'll talk about some preliminary work where we try to look at what catalogs exist and just trying to see how people tend to describe models in order to find them and work with them. But the starting point for that, we've been just looking at geospatial resources in general, data sets, catalogs, vocabulary, services, information models, anything that people in geosciences use when they try to find data, understand what this data is about, and integrate with other types of data. So our system is, as I said, mostly focused on data sets. We have a bunch of external catalogs, and we harvest information from these catalogs, put this into some kind of staging database, because when you harvest information from multiple different providers, it is a mess. They all use slightly different, even if they all claim that they use ISO 19115 or use 19139 schema, that is a schema that is XML schema that describes how you use resources, how you describe data resources. Then there will still be a lot of variations, and some fields will be not matching, some fields will be missing, some fields will be formatted differently compared to, differently across sources. So we need to kind of stage this data and then see how we can process it in a way to make metadata consistent. So there is a bunch of metadata enhancers that will look at it record by record, see what is missing, and try to figure out how it can be remedied. And then we republish the data. But now let's look at the models. And many of you have heard of integrated environmental modeling concept, right? Yes. So the idea is that you have a bunch of modular resources that you can combine into modeling processing chains and more complex models. And this is one of the ideas of DRIHM as well, right? You have modules with well-defined boundaries that you can, with well-defined APIs that you can plug into a system such as OpenMI or other types of integration environment and run a more complex model where these different model components would exchange data at each step or at some other. In order to make this happen, we need consistent descriptions of these modules, and we need to have a way to find these modules. And the problem is that there are lots of models that they have been developed outside of such frameworks as DRIHM, and there is significant effort required to make them DRIHM compliant or OpenMI compliant or compliant with any integrated environmental modeling system. And there are very few catalogs. So we looked at catalogs that are CSDMS. Have you heard of that? Community Surface Dynamic Modeling System. That is a catalog of geoscience models that is maintained in Colorado, funded by NSF, and they have about 170 or so models. EPA has models, NOAA has models, then there's a project, there was a European project called TESS. I don't know if it exists yet. Anybody heard of it? All right. So if you look at them, CSDMS, you can go to CSDMS webpage and see that they have a bunch of models. The types of metadata that they use to describe models is actually pretty good set of characteristics and fairly consistent. The problem is that when you start entering this information in model questionnaire, you will end at and then see what you end up with. There are lots of fields that are blank, so it's not a very consistent coverage. It's not quite clear in many cases what is being asked, and there are some things that are especially interesting for modelers, but they are very difficult to extract from people, such as description of the physical processes, model testing. So ideally, when you want to reuse a model, you would want to see if this model has been tested, under what conditions, and so on. This information is typically missing. And there are also many different types of models there. We tried to Google and just count the number of hits for some of the models in CSDMS, and it turns out that you can find WRF, and it has like hundreds of thousands of hits, and then there are a bunch of models that have maybe 10. EPA is a totally different animal. Here you have models that are not necessarily contributed by authors. These are models managed by EPA for certain regulatory reasons, for certain regulatory purposes. As with most other catalogs, information is not filled out consistently, but they have some unique fields because this group is supposed to manage models. They want to figure out what is the stage of the life cycle of the model, if this model is about to be discarded, or if this model is development in operational use, and so on. What kind of user qualifications are expected, and what specific operational or regulatory status are being addressed by the model. This is different from how models are described in academic sources. NOAA they don't actually have a web-based inventory. That was just a PDF file that was given to me under conditions that I don't share it around. But they promise to change that. This policy eventually, because this is actually a very nice collection of models. But this also raises the question, what is a model? When we refer to a model, do we refer to a modeling engine, or do we refer to an instance of a model? Do we refer to some kind of activity associated with modeling? Or that would be a collection of runs. So NOAA has been very explicit about talking about modeling activities. Each of them is characterized by a specific budget. I guess that was done mostly for budgeting purposes. And because it was done for budgeting purposes, they have all information filled out very consistently. There is not much of it, but all these 427 models or modeling activities are described very well. However, if you would be looking for WRF here, you would find maybe a dozen instances of WRF-related work. WRF chemical, we were looking at it yesterday, right? And there were a few other things. ESMF is yet another has yet another catalog of models, And this is yet another perspective of how you organize model catalogs. Because here the focus is on a framework in which different models can be integrated and run together. ASMF stands for Earth Systems Modeling Framework. So the components here are described from the perspective of how they connect with each other. What are the integration hooks that are embedded in each model to make it work within the system. In fact, models are referred to here as components, and the focus is what is the context in which this component can be run in conjunction with other models. And finally, another collection of models. When I looked at it last, there was 393 models. A European project called TEST, they just put up a web form asking people who are associated with the project or found the web page to and have developed a model to fill out that form and describe that model. As you can imagine, there is a lot of very heterogeneous stuff on this page. Sometimes models are referred to as some, there would be a WRF entry perhaps, and there would be an entry for an Excel spreadsheet. Right? So these are very two different animals. I'll show you how you can look at some of these things. Okay, so this is a collection of test models, and you can zoom in and look at the descriptions. There are some interesting interesting ways of how you can analyze it. So this is, for example, distribution of models by platform, models that use grids or internet-linked servers or single computers. You can look at, let's say, models that take hydrologic data as input and that work on physical hazards. Now, since I did not compile the catalog, it's up to you to interpret and see if I can recognize some of the models. I believe it kind of derives from European Commission requirement to always give a short abbreviation to whatever project you submit. So this project end up to be names of the models, and they may not necessarily mean much without like a long phrase that describes what this model actually does. Yeah, so what you see here on this side is so-called faceted search interface, where you can select some facets or components and then look at how models are distributed on any of the other components. Let's say we're looking at sectoral distribution, which models are used for research, education versus management. If you look at models, let's say this is a collection of NOAA models included in ASMF, I believe. And you can search for WRF here. And see there are some WRF entries. Anyway, the point I wanted to make here is that this is an easy way to look at not only just browse the models and see how many of them are there. Altogether, we maybe have a thousand of different models, but as I said, the ways to describe metadata in these models are totally inconsistent, and it requires some mapping, ideally to a common schema, and that's what Quallen will tell you more about. Here, it's mostly a way to look at deficiencies in model descriptions and compare these deficiencies across different providers. Going back. Oh, by the way, this is all on the web, so you can try to play with it. So what we try to do is to look at commonalities and differences between different model catalogs. There are some characteristics that exist almost everywhere, like you can find model name and model category, purpose, model type, some brief description almost in all catalogs, but then it becomes very different, especially when you are trying to look at science use case. Ideally, you want to when you're looking for a model, you would want to understand what type of problem it addresses. That is described consistently by CSDMS, which is an academic system, and to some extent by EPA, and there's also, it can be mentioned in the TESS model as well. But then other things like key model assumptions, applicability limits, spatial temporal dimensions, these may be described quite inconsistently across different modeling catalogs. Supported platforms, programming languages, some of the systems describe them, others are not. This is a section on inputs and outputs, and you see that unfortunately most of it is blank because model catalogs do not or typically do not provide this information. This information is very critical if you are trying to build a system like DRIHM, where you want different models to exchange information at every step. Not to mention that some things like uncertainty estimates for output, forcing initial conditions, boundary conditions, data quality requirements for input are present nowhere. So none of the catalogs that I found actually includes any of these things. And a few things that we thought would be useful to have, they are generally not captured by the catalogs. So that points to kind of conclusion that DRIHM is actually quite ahead of its time. We're at a fairly early phase in development of model registry and model coupling procedures. Because the existing catalogs and existing systems for model descriptions are very incomplete and insufficient for doing what DRIHM is trying to do. That is because different collections of model catalogs have been developed for different purposes by different groups, and their manner of collecting this data is also quite different. In our case, well, that was actually why we looked at data. As I mentioned, I'm not a modeler, but we looked at model data as a way to figure out what are the use cases that would connect different geoscience domains. If you look at, yeah, this nice picture. So this is a collection of models mapped such that, let's say, these are all hydrologic models, and this line represents a number of models that take data from this field. Right? So if you look at meteorology models, they may take data from agriculture, from spatial data, from soils, from some other domains. So the size of these lines would tell you interconnectivity between different domains in the Earth sciences. Okay? Ideally, that would be done from a collection of use cases that we can say, well, these are cross-domain use cases, and we can figure out what are the data flows within such use cases. But there are no good inventories of that, so we used models as proxies. Yeah, I think I'm getting to the end of my time anyway. And this was some conclusions about model catalogs. We have to deal with different semantics and different templates for model registries, which makes it very difficult to make a joint catalog. The scopes and intents of inventories developed by different groups is quite different. For DRIHM, it will also be different from all of the above, but DRIHM has a chance to develop a system that would be based on ISO standards and will have therefore some longevity, and again I'll let Quillan talk about that later on. The feeling from this particular work was that standardization in model descriptions may be a little premature because of different registries are such all over the place, and purposes and ways of describing models are so different. But one way to help matching the different approaches would be just to visualize the catalogs and see what the deficiencies are. And I showed some visualization tools. I think I ran out of time, and we covered a lot of ground. So I can go back and show you a bunch of XML, or we can rather switch to questions. Questions would be better, because I've been talking for an hour, and that's impossible. Questions? So we talked about model catalogs, data standards, data sharing. Too much information?
Is there any option or you're thinking to connect into the GTS data from the WMO, because you are also collaborating on WMO hydrological platform? But as GTS has contains all the global observation systems.
Right. So we've been actually talking with world data centers and several WMO groups, and the idea is if we can, if they publish, let's say, CSW catalog with information about what can be obtained from, then we can easily harvest from them. So on the technical side, it should be quite possible. Semantically and organizationally, it's less clear. Okay. Go on.
Well, I was going to ask you, Ilya, what do you think, as far as the DRIHM project goes, what are the key challenges that we are going to face now we have nearly delivered a complete DRIHM system? You know, we have a catalogue, we've got all the models prepared, we've got workflows sorted out, we have a portal, which we'll show a little bit later. As we start getting into the phase where we want people to really start using it and to grow it into different domains, what do you think are the challenges that we will face as we start to do that?
That's a very good question. One big challenge is to try to track consistently what worked and what didn't, so that you have some mechanism to steer the development. If you can analyze logs of models, capture provenance of any decisions that are being made, and if the modeling actually made an impact on operational decisions or forecasting decisions, that would be very good. Also, if you can trace what didn't work, I think that would be a very important component that is often overlooked in development of information system, that kind of feedback system. From what you describe, and I'm not an expert on DRIHM, but it sounds like all the main components are in place. There are a few emergent components that will need to be, that are typically outside of the development of cyber infrastructure, and they deal with, besides feedback loops, they deal with social networking, they deal with collections of use cases and seeing how what you develop maps to specific use cases. is trying to come up with standards compliant model descriptions and model chaining. I see this would be like the most interesting directions from my perspective, but at the same time I'm neither Antonio nor European Commission, so it doesn't really matter. Okay? Thank you very much.